let's revise. There's two kinds of progressions that we're interested in this topic, right? APs and GPs. What does GP stand for again? Good. Now, what makes a GP as opposed to an AP? What's the characteristic that it has? That's right. So as you go from term to term, you're multiplying by something over and over and over, right? Now, after we wrote that all out, we came up with a formula for the sum of a GP, right? With a given first term, a given ratio, and a given number of terms, right? Can you rehearse for me? What's the formula? A times
R to the power of the number R to the power of that
yep.
minus 1 over R minus 1.
Yep, good. Okay, now we also noted there was another way to write this, which was to flip around the numerator and the denominator. Okay, now to come things a little bit short, if you want a more detailed explanation, you can go watch the video. I want to consider the very special case where the ratio that you've got doesn't make numbers bigger, but makes them progressively smaller. Okay, so if our ratio was 2, for instance, your numbers are going to increase in size, right? But if your number is a half, sorry, if your ratio is a half, then your terms are going to decrease in size, and so on, right? So I want to consider this case, this second case, right? As a catch-all, the kind of restriction that I want to place is the numbers are going to decrease so long as the ratio is between -1 and 1, okay? If the ratio is outside those boundaries, if the ratio was, say, -2 or 15 or anything outside that domain, then the numbers aren't going to shrink towards something, okay? They're just going to keep getting bigger and bigger and bigger, whether it's positive or negative, okay? So this is the kind of domain I'm interested in, which alternatively, if you want to be fancy, you'll sometimes see written with absolute value. Okay. Now, I just want to focus on this term up here. Okay. I want us to think about this. For a series like these, which have no end, right? What would happen, what is going to happen, as I consider the sum of the whole GP, right, as, this is over here, as n approaches infinity. I want to try and not just consider the first 50 or 100 terms. What if I could try and consider all of them? Okay? What would happen? Now, have a look at this guy. Okay? R to the n. Okay? I'm going to use our language from calculus to try and say, well, what's that going to approach as n approaches infinity? As I climb off to enormous numbers, 1 million terms, 1 billion terms, and so on. Okay? Now, it's going to approach 0, but the question is why? Why would it approach 0?
Because when you multiply fraction by something gets smaller.
Yeah, exactly right. And you can see that happening. Let me just repeat that. When you multiply a fraction by itself, it gets smaller, and this kind of demonstrates exactly what's happening, right? And it's shrinking quite fast, isn't it? So, therefore, if this part of this is going to 0, right? If I apply that limit to the whole lot, limit as n approaches infinity of the whole sum. Okay? This is going to be the limit as n approaches infinity of this. Okay? Now look at those terms, right? As n approaches infinity, what happens to a? Nothing. It just stays a, whatever that first term was, right? What happens to 1? Nothing. You see where I'm going, right? If there's any term that doesn't get affected by n, which isn't connected by n, right, to n, nothing happens to it, which includes these guys down here, these guys down here. Now you see why I was focusing on this. We've just established that it approaches 0, right? So if I evaluate my limit out, it's going to be a times 1 minus 0 on 1 minus r, which is this. Okay? Now, because there's an infinite number of terms, right? It's sort of tempting to call it the sum to infinity, okay? But that's a bit shifty. N is meant to be a number of some kind, right? And we've established before that infinity is not a number. It's a useful concept, but it's not like you can sub it in and get something meaningful out of it. So they just call it capital S. Okay. Yeah, they shouldn't. They really shouldn't. For the reason I just said. So this, put a big box around it, this is what we mean by the limiting sum. Can you see why it's called limiting, by the way? Because it has to do with taking the limit as n approaches infinity, right? Okay, now, you who were here yesterday, I'm almost caught up to you, okay? But I want to illustrate this to everyone, and then we'll look at the series that I challenged you with at the end of the day, okay? This series up here, right? What's it going to equal to? It behaves, according to these rules, the ratio is between -1 and 1, it's a half, which is fine, okay? So using this limiting sum formula, what would we get as the answer? Let's try it out. The sum is, now what's the first term in this particular series? It's 1, right? Divide by, now, what's the common ratio? It's just a half, right? So it's 1 minus a half. So that's 1 divided by a half, which is 2.